Again, welcome to College Algebra. In these lectures, we're going to discuss more on functions. Here, we're going to focus on the piecewise defined functions. So our main objective is to determine whether a function is even, odd, or neither. Again, we are going to determine whether a function is even, odd, or neither. Also, we're going to identify the open intervals on which a function is increasing, decreasing, or constant. Also, we are going to identify local maxima and also local minima on the graph of a function. And also evaluate and graph piecewise defined functions. Also evaluate and graph the greatest integer functions. So first, we start with determining whether a function is even, odd, or neither. So we start with the even function. Now, if we have a function f at negative x and is equal to f at x, again, f at negative x equal to f at x for all x in the domain of the function, then we say the graph of the function is symmetric about the y-axis. And this function is called an even function. So if we have a function again, f at negative 2 equal to f at 2, and these two functions in the domain of the x values, the functions are symmetric about the y-axis, then the function is called an even function. Now, an odd function is if we have a function of f at negative x, but it's equal to negative f at x. Again, the negative, we still have negative f at x. Even function is when f at negative x equal to f at x for all the domain x. Now, if we have a function f at negative x and it's equal to negative f at x for all x in the domain of f, then the function is a symmetric about the origin. And this function is called an odd function. So if f at s does not have either x-axis symmetry or origin symmetry, then the function is neither even or odd. So let's see an example. Here they say we should determine whether the functions shown here, f at s equal to s squared plus 1 and f at x equal to s cubed, whether these two functions are even, odd, or neither. So we are going to test what makes a function even is if we have f at negative x and it's equal to f at x, then the function is even. So we are going to test it. So if we can find f at s is s squared plus 1, if f at negative x will give us s squared plus 1, then the function again is an even function. So we start with the f at negative x is the same as writing negative s squared plus 1, which give me s squared plus 1. So the function again is even because f at x is s squared plus 1. F at negative x is still s squared plus 1. So they are equal. So if f at negative x equal to f at x, then the function is an even function. Now b, we have f at s equal to s cubed. So let's try f at negative s. F at negative s will give us negative s cubed. Now negative s cubed will give us negative s cubed also. So which means it will give us negative f at x. So this function is odd function because odd function we said that f at negative x is equal to negative f at x. We still keep the negative. Now let's go to identify the open intervals on which a function is increasing, decreasing, or constant. So if we trace the graph of a function from left to right, so here we have a and b, and the values of f at x as shown in the figure is increasing, then we have increasing interval. If it's decreasing, we have decreasing interval. So looking at here, this graph here, we can see that the interval from a to b, the function is increasing. So the interval between a to b is increasing interval. Now, if we have a function f at s, and we have interval a and b, and from interval A to B, the function is decreasing, then we have decreasing on the interval. So now, if the values f at s remain unchanged as s increase, we say that the function is constant on the interval AB. So we have interval AB, and as the values are increasing, the function remain the same. Then this is constant function. Now, we are going to state the open interval on which the following function is increasing or decreasing. So we have from -5 to +5, and we have 0. We want to see where the function is increasing. So we can see that the function is increasing from 0 here where my cursor is. In this section is decreasing. Also beginning is increasing. So we say we can trace the graph of the function from left to right and identify the open interval which f at s values increase, where they decrease, and where also they decrease. So we can see that looking at the function here, at 3, 1, 2, 3, at 3, the function will be increasing. Then from 3 to 0, 2 to 0 is decreasing. From 0 to 2 is increasing. Then from 2 to 3 is decreasing. So we said that we see the graph that the values of f at s increases on the interval from -2 to 0, and also from 0 to 2, or -infinity to -2, and also 0 to 2. They decrease on the open interval from -2 to 0. So let's see. -2 to 0 is decreasing. This is the line. And from 0 to +2 is increasing. So the degrees on the opening, so we can see 0 to +2 is increasing. And -infinity to -2, which is the beginning, also is increasing. We can see from here, it's increasing from -2. So this means, hence, we have our function is increasing from -infinity to 2, and also 0 to 2, and it's decreasing from -2 to 0, and 2 to -infinity. Just by looking at the graph, we can see that from -infinity to -2, increasing, from 2 to 0, decreasing, 0 to +2, increasing, then from +2 to +infinity is decreasing. So that's what we say. Hence, the function is increasing from -infinity to -2, union to 0 to 2, and it's decreasing on -2 to 0 and union to infinity. So now next we are going to learn how to identify the local maxima and also local minima on the graph of a function. So if we have a function, let's say we call the y value of a high point, that will be local maximum, and we call the y value of the low point, which would be local minimum. So we have the local minimum down and local maximum. So collectively, we say that the term extrema, when we are referring to local maxima and local minima, sometimes they are also called relative extrema. So local maximum and local minimum. If I have a function f at c, which is local maximum, if there exists an interval AB with c less than b and c greater than a, such that f at s is less than f at c for all x in the interval a to b. Now, it's local minimum if there exists an interval AB with a less than c, c less than b, such that f at s is greater than or equal to f at c for all x in a and b, the interval AB. So a local maximum normally occurs when the function changes from increasing to decreasing. So it's at the top when the parabola open up downward. When you open upward, then we have a local minima. So local minima occurs when the function changes from decreasing to increase. So this example, so C1, we have local minima from decrease to increase. Then C2, we have local maximum from increase to decrease. So here they say we should locate the local maximum, local minimum using a graph of the function. So C3 will be local minimum, C4 will be local maximum. Now the point C2 and F at C2 and C4, F at C4 are where the high points occur. So that will be the local maximum. Maximum means high. So we have C2, C4, that's where we have two highest points. Now we observe that there are two low points on the graph. Therefore, we can have two local minima, which is C1 and C3. So we have C1 and C3. Now the point C1, F at C1, and C3, F at C3 are where the high points occur, but the local minimum are only the y values of those points. So next we evaluate and graph piecewise defined functions. So if we have a graph of function f at x, when s is negative x, then we have s is less than 0. When s is square, s will be between, the domain will be between 1 to 0. And if it's 1, that means s should be greater than 1. So this solution, this piecewise defined function is defined in 3 parts. So we have 3 different parts where we will again graph each part of the function. So we'll graph f at s equal to negative x. Then we have the interval from negative infinity to 0. Then f at s equal to s squared. The interval is from 0 to 1. And the last will be infinity. So if s also is less than 0 and the value of f at s is determined by the equation f at s equal to negative x, then we need to graph the line with the slope m equal to negative 1. And the y-intercept is 0 and b, which equal to 0 and 0 in the interval from negative infinity to 0. So if s is less than or equal to 1 or greater than or equal to 0, then the value of f at s is s squared. We can graph the squaring function in the interval 0 to 1. Then in the open interval 0 to 1, the function is increasing. Now, if s is greater than 1, the value of f at s is 1. So here's the graph of the piecewise function. We have our first term, a line, then we have part of a circle, then we have a horizontal line. Next, we're going to evaluate and graph the greatest integer function. So greatest integer function is important in many business applications and also in the field of computer science. So the function is determined by the equation f at s equal to absolute x, where the value of f at x that corresponds to x is the greatest integer that is less than or equal to x. So here they say we should graph f at s equal to absolute x. Now the solution here, we can say that we will list several intervals and determine the corresponding values of the greatest integer function. Then we will use these values to graph the function. So we start with f at s equal to absolute x, which is 0. Then f when it's 1, 2, we have 1. When it's 2, 3, we have 3. So this is the piecewise, again, how we plot it, each point on the x-axis. So that will be the conclusion of our lectures, and again, wish everybody the best.